Hey, everybody. So this little lecture is going to be about section 4.2, which is about graphing rational functions. This, I have I have some philosophical issues with this because, frankly, I think the way to approach graphing most things these days is to use the appropriate tool, use technology like Desmos or a graphing calculator. But the the book makes a pretty good point that there's some other stuff that you get under your belt by looking at this issue of graphing things by hand. And so yeah, I kind of sold on that. There's a what they call number sense in there, some ways of thinking about the values of functions near interesting points that well, we're going to want to see. So let's pop into the textbook and look at some of what they talk about. Um, First, excuse me 1 second. Nope. Darn it. I have the wrong thing. There it is. So, first thing we're going to do is think about sign diagrams. Basically, just keeping track of where is a function positive, where is it negative. Now, with polynomials, that's super easy because polynomials only potentially change sign when they have zeros. But for rational functions, the situation is more complicated. Um, here's a particular example. I don't know which function they've plotted here. Well, it kind of doesn't matter. You see, it's got a vertical asymptote at -1. It's got a 0 at 1/2, and it's got a hole at +1. Um, those locations, both the vertical asymptotes, the zeros, and the holes, are potential spots where the sign could change. Now, in fact, the sign does change. You see how we go from below the axis to above the axis at the 0? And at the vertical asymptote, the sign does change. It's going towards plus infinity to the left of the vertical asymptote, although on the right side of it, it's heading towards negative infinity. So the sign is changing a lot. At the hole, nothing happens. It's positive to the left of the hole. It's positive to the right of the hole. So no big deal. Well, here's the sign diagram, and they're advocating for this weird symbol where you put a question mark and an exclamation point together, which I'm told is called an interrobang. But whatever you put there, I mean, you're welcome to use that symbol. I usually just put a little question mark. These are places where we don't really know what the sign is, or in a sense don't care. But in between those funny spots, we can tell what sign we've got. So the funny spots occur at -1, at 1/2, and 1. Oh, well, at 1/2, we actually do sort of know the value of the function because that's a 0. So rather than an interrobang, they wrote a 0 there. The little pluses and minuses in parentheses are just you pick a value in there and you test and see whether it's positive or negative. Since it won't change anywhere except at the marked positions, it's like, for instance, positive in the entire interval between 1/2 and 1. And it's negative on the entire interval between -1 and 1/2. Well, that and I guess I want to contrast what's going on there with the situation with polynomials. So let me pull in our document camera. When you have a polynomial, there's sort of two elements to the things you think about. That's a little picture, sort of the graphing calculator window or the Desmos window. Inside of here, there's potentially zeros. Well, that's really all that happens with polynomials. You'll have zeros inside of there. But outside of there, you'll have what's called the eventual behavior. So you might think about the polynomial has features on it that are part of what's called a local picture. And then it has global behavior, which is these two arrows. If we move to a rational function, the local picture and the global behavior both get more complicated. So what does it look like with a rational function? Well, just as an example, here's the graphing calculator window. You can have zeros, you can have holes, and you can have vertical asymptotes. These are all features that will happen, and you'd see them in all of them happen around kind of the middle of the graph. The eventual behavior, well, I should probably draw the axis on here. The zero is a place where the sign can change. The hole actually is a place where the sign can change, although I've drawn one that doesn't. And the vertical asymptote is a place where the sign can change. I'll have it change like that, for instance. You can analyze this local picture very quickly just by factoring the top and the bottom of your rational function. But what happens outside the global picture? That's a weird way to misspell that. Global behavior. And we've seen some of the global behaviors that you get out of rational functions last time. For instance, you can have horizontal asymptotes. Maybe it's a horizontal asymptote at zero. It's also possible that you get slant asymptotes. Outside of this picture, we'd approach a straight line. It's even possible to get behavior that looks like a polynomial did. Polynomials are up here. You could have, for instance, curving upward and curving upward out of there. And our job is basically to work out all of these. Figure out the zeros, the holes, and the vertical asymptotes, and get sort of a center of the graph picture. Also figure out what's going to go on globally, what kind of asymptotes we have, and put all that together into a cohesive picture for what the graph will look like. And then frankly, I'm going to go back to Desmos and check our work on that. So, oh yeah, there's one point I should have made. These locations, the zeros for a polynomial, they didn't have to have a sign change there. For instance, it'd be possible that this is a so-called double root, and the polynomial would hit that and bounce off, in which case its global picture would go downward from there. So you can have a place where you potentially could have a change of sign, but it doesn't happen. Well, that's true in the rational function case too. In fact, the behavior of the zeros is very much the same as the behavior of the zeros is for polynomials. So you can have a graph that has a double zero, and then it doesn't change sign there. The asymptotes can behave that way too. You may have a graph where let me just try to give you an example of that. You could have a graph with a double zero and also a double asymptote. It goes up to that vertical line, and it comes down from that vertical line. And then maybe it has a regular zero, who knows. So there's a local picture of something with some pretty funky behavior. Anyway, the point is, we needn't necessarily change signs. That's just the places, those asymptotes and zeros are the places where it could. And the sign diagram for this one would be plus here, plus there, and only minus when we get to that last bit where it crossed through it had a zero that it actually crossed over the axis and changed the sign. Okay, so I got a note to look at the boxes on page 321. So let me find the boxes on page 321. Oh, there they are. It gives you sort of a step-by-step way to think about making sign diagrams, and then once you've got the sign diagram, you come back and by hand make a graph of the rational function. Now, doing this by hand will get us close most of the time. There are issues that you won't pick up about the graphs of rational functions until you do calculus, but a great deal of the general shape of the thing will be something we can produce by hand. All right, so let's see. What do we do to construct the sign diagram? So first, place any values excluded from the domain of R on the number line with an interrobang over them. find the zeros of r, and that'll be the zeros of the numerator, and place them on the number line with the number 0 above them. So a bunch of dots on the number line so far. Choose a test value in all of the intervals you've just determined. Each of those things splits the real line up into a bunch of intervals, right? And we're just going to find a test point in each of those intervals and calculate the sign. It's not going to change except at those critical points, those points that have the question mark exclamation point thing on them, or the 0 on them. And so you get a single sign that you can use for those entire pieces of interval. Okay. We'll go through that process on an example in a second, but then let's continue on and talk about how to graph the rational function. So first, locate the domain, which is mostly looking at the denominator and saying, where is the denominator? 0. If you have common factors in the numerator and denominator, go ahead and cancel them out. Just don't forget that the domain is still affected by the places where those common factors would be 0. Find the x and y intercepts. Well, that's reasonable, right? At least that's stuff that's fairly easy to calculate. X intercepts, those are the zeros, which are going to be zeros of the numerator. Y intercepts, those are, well, that's just the value when x is 0, so that's super easy to compute. Just plug in 0 into the function. Then look for any vertical asymptotes or holes. Those are places where the bottom is 0. Vertical asymptotes are where the bottom is 0 and the top isn't. Holes are where both top and bottom are 0. And then we're going to look at the behavior of r on either side of those. It may not be necessary to, but just for the sake of developing a sense of how to do that, we will look at that. And finally, analyze the end behavior. See if there's a horizontal or a slant asymptote. See if there's other kinds of asymptotes. We'll use a sign diagram, and if necessary, we might plot some additional points. Normally, it wouldn't be necessary. And then we'll just sort of fill in the graph in between all the features we've identified. All right, so the first example they go through in the book here is a pretty reasonable one to look at. I'm not going to follow along just by reading the book, though. Let's do this on paper. So the rational function involved is called it f of x, and we'll stick with that notation. F of x is 3x divided by x squared minus 4. Oh, I feel like I'm gonna be referring to that list of procedures, things to do while we go through this. So the first thing is to find the domain of the function. Now, what is the domain of this thing? You just look, where's the bottom 0? And that's when x squared is 4. I think I'm going to go a little quick on this. Do you see that it'll be plus and minus 2? So we'll have a domain that goes from minus infinity up to minus 2, skips over minus 2, and then heads from there up to plus 2, skipping over that, and finally from plus 2 to infinity. Right. We're going to reduce r of x to lowest terms if that's necessary. Do you see any factors in common between these? I guess if you want, I can factor the bottom for us. The top is already in factored form. The bottom turns into x plus 2 times x minus 2. So there aren't any common factors, so that piece is already done. Intercepts. Can we locate those? Well, the top is 0, sorry, just at 0. So the x-intercept, I'm sorry, this is written so sloppy. X-intercepts, x-intercept, and, okay, I'm making lots of weird stray marks on here, but just take away one of them there. The x-intercept, it's just the origin, 0, 0. It turns out that's the only y-intercept there is too. If you plug 0 into this function, you're going to get 0 in the top and negative 4 in the bottom. So 0 over any number is 0. So the y-intercept is also 0, 0. All right, and then vertical asymptotes. There's one at -2 and there's one at +2, which you can see from the factored form of the denominator of that thing. So that's what we've got to do. Find the location of any vertical asymptotes. All right, at this point, I'm ready to kind of draw in a loose schematic of what the graph looks like. Here's the x and y axes. The x and the y-intercept are at 0, 0. So that's a place where the graph crosses the both axes. The vertical asymptotes happen at -2 and +2. And so we'll have vertical dashed lines above those positions. All right. And then, we should analyze the end behavior of this thing. That is, this picture is going to be what we might see inside the graphing calculator window. Well, what's going to happen after we move way out this way, or way out this other way? All right, so what is going to happen? Well, let's look at the formula again. The top is a degree 1 polynomial. The bottom is a degree 2. When you put numbers like 1,000,000 or 1,000,000,000 in there, it seems like you have a very big number in the top, but you have a much bigger number in the bottom, the square of that one. So this will be big over way bigger, and that means it's basically 0. So that thing's going to have horizontal asymptotes heading towards 0. I don't know whether they're from above or from below at the moment, but they're heading towards 0 for sure. All right, let's see if we can figure out the sign of the function at some places in here so we can work with that. Here's a nice one. In between the 0 and the vertical asymptote on the right-hand side, we've got a test point x equals 1 that's just begging to be used. And again, returning to our formula, we don't even need to figure out what the value is, just whether this is positive or negative. So is it positive? Well, the top is positive. It'll be 3 times 1. But the bottom would be 1 squared minus 4. That's a negative number. If you've got a single minus sign in it, that means in here we're negative. Right? How about there, in the other interval formed between a vertical asymptote and an intercept? Well, that would be -1, and the numerator would now be -3, and the denominator would also be -3, because -1 squared is +1. So those things cancel, and we end up with something with positive in there. Can we get some more test points and figure out what's the deal outside of here and outside of here? I guess the smallest number I could put in would be, for instance, 3 on this side and -3 on that side. Look at the formula again. If we're at the positive side, where we're getting +3 in there, we will have 3 times 3, 9, divided by 9 minus 4. Well, all I care about is that's 2 positive numbers. Numerator and denominator are both positive, so yeah, we're going to have a positive thing out there. And what about the other side? Same thing happens in the bottom because of that squaring, x squared minus 4. So you get positive 9 minus 4, which is a positive number, but the numerator will be negative 9. So it's going to be negative out this way. Well, that's pretty much enough info to completely seal this thing's behavior. We're going to pass through the origin, going from positive to negative. We're going to head towards that vertical asymptote, head off to infinity that way. But we're going to change sign at the vertical asymptote, which means we come back in from the plus infinity side. And then we head towards 0. On the back end, this thing's got nowhere to go but up. It goes towards the vertical asymptote, towards plus infinity. The sign changes, so we know it comes back in on the other side from minus infinity. And it's got to head towards 0 in the overall or end behavior of the thing. So that's that's pretty good. Let's come back to the looking at it in the book and see what they tell us. Well, I mean, they went through the same stuff, but when they finally get to an answer, and it looks it's neater than mine, but it's more or less the same shape as what I had. There is something they did in here, though, that I want us to look at, and it is in closely analyzing the behavior near these vertical asymptotes. So I'm just going to do one of their little examples of how you develop a number sense about what happens as you go towards one of the asymptotes. Where is that? Okay. So they're looking right on in this paragraph about about x approaching the number -2. So that left-hand asymptote. As x gets closer to -2, the smaller x plus 2 will become, because -2 and 2 are they cancel. You get 0. So we're going to have a thing that when you look at the factors has, well, numbers that are approximately, that's why that funky equal sign is in there, approximately at -2, the top is just -6. Again, approximately. The bottom has 2 bits in it, though. The x minus 2, if x is close to -2, you're going to get -4. If x is close to -2, oh, well, watch out what they're doing with this arrow thing here. This says x is approaching -2 through numbers that are smaller than -2. That's what that minus thing means. So the number we're getting isn't 0 exactly, but it's a very tiny negative number. All right? That's the analysis you'd want to do near an asymptote. You'll have pretty close to actual values for some of the things, but then other numbers that you're just going to call very small minus or very small plus. Right? So in this case, we're approaching x is -2 from below, and we get -6 over -4 and something very tiny that's negative. You see how 2 of those minus signs will cancel? We end up with something that's negative. But how big is that negative thing? Well, the 3 and the 2 are just regular sized numbers, and this thing, this very small negative number, can get as close to 0 as you want. We get approaching the role of it going undefined, where we're dividing by 0. So we've got something that's negative, and that's huge. A very tiny number in the bottom makes the fraction gigantic. That's the kind of number sense the book is referring to, and that I think is pretty important for you to develop. That you're able to think through, what's going on as we look at very small numbers as we look at x approaching a particular value and creating factors that are very small, either negative or positive numbers. Well, that analysis that they do a little more carefully let them figure out the shape of the asymptote from that idea, rather than just, I did it via, we're on the plus side and it's got to be going up, or here we're on the negative side and it's got to go down to hit the asymptote. They worked out these things without reference to the sign. All right, that's pretty good. One more example I want to get through, and it's one that I cooked up that's pretty ugly. So just to show you that we've got the power now to get through some pretty crazy hard looking rational functions. So here we go. So I put this in Desmos, and I made a P and Q. I actually had it plot the P and the Q separately, or define functions P of x and Q of x, and then to get the graph I just plotted P over Q. Now that's weird looking, right? It just looks like a cubic polynomial, but one of the things that you probably get used to as you do more and more rational functions is zoom out a little bit and see what else there is, because there usually is. Oh yeah, okay, this thing's got some wonkiness to it, doesn't it? So in tight, in that close-in local picture, we had just a thing that looks like a polynomial. But if you get away far enough, you see there's a vertical asymptotes in there, and there's, oh gosh, it's got a slant asymptote, the eventual behavior. So let's try analyzing this thing. Let me turn it off for a second and plot its numerator. Well, that numerator it's pretty irreducible. It's only got 1, 0, and it happens with multiplicity 2 right there at x equals 1. So that means x minus 1 is a factor of it. And that means I'm going to have to do some dividing. But let's do a synthetic division. And oops. The thing I need to synthetically divide is the numerator of my polynomial. Whoops. The numerator of my polynomial was, I gotta watch where I'm drawing on this so you see me. There we go. X to the 4th minus 2x cubed. Oh, I'm accidentally doing long division. That's always my habit. Plus 2x squared. I meant to do this by synthetic, but maybe we'll do the next one synthetic. So just copy the polynomial in there. The term we realized from the graph is a factor of this was x minus 1. Right? And so we'll go through division here. X goes into x to the 4th, x cubed times. X cubed multiplied back gives us x to the 4th minus x cubed. This is one of those weird ones, hard ones, where we're subtracting a negative, so that's really adding x cubed. Minus 2x cubed plus x cubed. That's just minus 1x cubed. And then the other terms can be brought down if you like. It's enough to do just the next one. X into minus x cubed gets us negative 2x squared. Multiplying back, we get, what did I do wrong? No, it's just negative x squared, not 2. Negative x squared. Yeah, there's an error check on yourself. When you multiply back, you're supposed to get a number underneath here that would be exactly equal to what's above. So negative x squared times x, that works. Negative x cubed here. Negative x squared times negative 1, that's positive x squared. Now when we subtract 2x squared minus x squared, that's just going to be x squared. X goes into x squared, x times, that's plus x. And x times x minus 1 is x squared minus x. That's kind of cool. When we subtract there, we are going to get negative 2 plus 1. So we're subtracting a negative. Negative 2 plus 1 is negative 1 x. And then there's a plus 1 down here. Now, that's maybe hard to spot, but that's exactly negative 1 times this guy. Well, anyway, the x into the minus x gets us a negative 1. And if you follow through the bitter end of the process, you get negative x plus 1. When we subtract that from what's above it, you get 0. Which had to be the case, right? Because we had identified a factor of the thing. Cool. Well, that means I now want to return to my Desmos and see about that polynomial. So I'm going to turn this guy off and plot, I don't know what to call it, f of x, I guess. It's what we get when we take p of x there and divide it by x minus 1. So it was the quotient we just found. X to the 3rd minus x to the 2nd plus x and then minus 1. Oh heck, that's got a 0 too. And it's also at 1. That means I can divide x minus 1 into that quotient we just got a second time. Here's where I better try to do it. I meant to do it by synthetic division, so that's what I'll do next. All right. So let's see. The polynomial I got just now as the quotient needs to be further divided by x minus 1. That means when we set up this synthetic division tableau, that'll be a 1 on the outside, because it's x minus the number that you see there. The thing we're dividing by has coefficients 1, minus 1, 1, minus 1. That's cute. I didn't notice that it just alternated like that before. All right, we bring down the 1. Then we multiply 1 times 1 and get 1. Then we add and we get 0. Then we multiply and we get 1. Then we add. Wait. 1 times 0. I got 1 times 0 and got 1. No, silly. 1 times 0 is 0. And then we add and get 1. And then that I only caught myself because I know what the answer is on this one. Sorry. Anyway, 1 times 1 is 1. When we add there, we get 0. It's good that we got the remainder 0. And this sequence of coefficients means the quotient is x squared plus 1. That's why I knew something was fishy, because I knew I was going to get x squared plus 1. I cooked this problem up after all. Yeah, okay, so now we have the numerator of that thing factored. It is x squared plus 1 times x minus 1 squared. This is an irreducible quadratic, and that's a pair of equal, but a pair of linear factors. Let's transition back to our Desmos and just verify that, which is, I want to plot, instead of f of x here, let's have a new thing be what we just worked out. X to the second plus 1, the irreducible quadratic, times x minus 1 to the second. Now, does that graph look the same as this graph? Yeah, they're identical. So that's a good way to check whether you factored correctly. You should end up, the factored form ought to look identical to the original guy. How about our denominator? Can we factor that? Well, let's turn off these guys and take a look just at the bottom polynomial. Well, now that's I guess I need to zoom out a ways. I kind of don't want to zoom just the both axes, so let me zoom Y so that it looks more reasonable. Okay. All right, I can spot some zeros on this. It's 0 at -3, at +1, and at +4. That would be 3 linear factors if we could get them out. And you know what? I think this is a cubic polynomial, so it's only going to have at most 3 factors, 3 linear factors. So this is a nice cubic polynomial with 3 zeros in it. I can just verify that the 3 zeros are what I want. You don't have to do long division if you've sort of found everything. So let's do a little multiplying and verify that we in fact get this answer when we multiply those guys out. Do that on our DotCam too. The factors we got, we can see on that graph are x plus 3 to get the one that happens at -3. X minus 1, and then x minus 4. I'm going to multiply those two first, because I can just quickly do a FOIL rule there. We'll get x squared minus 5x plus 4. I did that so we could set up a table method for the other bit. X and 3 are the row headings. And then I'll fill out the table quickly. There's an x cubed, a minus 5x squared, and a 4x there. 3x squared goes here, minus 15x, and plus 12. So let's gather everything together and write down the well, combine the like terms and write down the final point of the polynomial. It is x to the third, that's the only cubic term. There's two quadratic terms. Remember that trick about how the like terms appear on diagonals? So we get minus 2x squared. And then minus 15 plus 4, that's 11, minus 11x, and then 12. That is indeed exactly what we had in the Desmos thing. X cubed minus 2x squared minus 11x plus 12. We can also do what I suggested is before, verifying or factoring by plotting both the original and its factored form. But, that's not going to be terribly interesting. Now, the whole reason we went through all of that was just to get at what does the graph of the rational function look like. So let's get back to the DocCam, and we'll do that. My sort of local picture first. We had a numerator that is 0 twice at -1. So that's going to, that's at +1. It's when the factor was x minus 1 squared in the numerator. So we got a 0 there. The zeros in the denominator, well, those were easier. We had another one here, which means I got one of those symbols at that spot. I don't know what's going on there right now. But we also had -3, a 0 in the denominator there, and then +4. This was at 1, so my scale was a little funky. You know, that's bad enough that I want to start fresh. At 1, we have this unknown position. At -3, we've got a 0 in the bottom. And then at +4, we've got a 0 at the bottom. Well, those mean vertical asymptotes. Zeros in the denominator that are not matched by zeros upstairs. What's going to happen when x is actually equal to 1? Let's take a second and go back to Desmos and see if we can find out. Here's the graph of p of x. Oops, I'm trying to click on the wrong thing, excuse me. Here's the graph of p of x over q of x. Let me turn off the other bit. Can we tell what its value is at 1? It seems to be 0 there. It's not 0. It looks like it's 0 at the origin, that the origin is an intercept. But if we zoom in enough, you'll see that it is not. Yeah, see, we're slightly above 0 there, but we are 0 right at 1. That's a hole, it turns out. We've got the numerator is 0, the denominator is 0. I wanted you to see an example where we can change sign at a hole, is really what's going on. So, yes, we have a 0 with a hole on it where I was unsure before what happens. We got two vertical asymptotes here and here. Let's find some test points and decide whether we're positive or negative in between these features. Now, x equals 0 is always a good test point to use. And if you jump back and take a look at what the polynomials were, p, when you stick x equals 0 in, is going to give you a value of +1. And q, when you stick x equals 0 in, that's going to give you a value of +12. It's a small number, but both things are positive, so you're going to get a positive number there. That means in here we'll have positive values all the way between this vertical asymptote and that hole. What about when we're at some of the other positions? Well, I think I'm going to let us get that off of the graph. we had a 0 at 1. So you can see that when you get on the other side of 1, the thing goes negative, right? In fact, it's heading towards a vertical asymptote, so it's going to get really negative in a minute. Okay, so that means, let's see, I need to put the dot cam back on and just write a minus right in there. Right? We're going to have negative values on our graph there. We could do a close analysis at the vertical asymptotes, but it's also somewhat quicker to notice what are the multiplicities of these vertical asymptotes. The factors that cause the vertical asymptote, if they occur twice, will make it be an even VA. Or a lot of times people call these poles. If I slip up and say poles, I'm talking about one of these straight up lines that the graph approaches. If the multiplicity of the 0 that creates this is odd, you're going to have a sign change. And if it's even, you won't. And both of these poles are odd poles. So you're going to go from minus to plus on the other side of it. And this one was plus, so it'll be minus on this side of it. Now, what about eventual behavior? Well, again, looking at our P of x and Q of x from when I originally defined them, you see the numerator has a higher degree than the denominator. So that tells you that it's going to have a slant asymptote because the degree is 1 greater. The degree of, basically, as x gets to really gigantic numbers, the fraction of these two things just looks like x to the 4th divided by x cubed, and the other stuff is much smaller than either of those, so it kind of cuts out. Well, that's probably a good place to leave it. The analysis we just did shows us all the features of the graph we've got on here. Let me put us back on our home screen and then zoom out just a ways. We found the vertical asymptotes at +4 and at -3, which we could throw on the graph if you like. We found the 0 at 0, where there's actually a hole, and I can't figure out why Desmos hasn't noticed this, but that's a hole, not a regular point on the graph. And then we've got our slant asymptote, which is not exactly just x. If I do that for you, if we just plotted y equals x, you'll see that it's close, but that is not approaching it the same way on both sides. It's actually getting, maybe it is just x, because it sure looks good. Well, how would we find out what that asymptote actually is? We'd have to do long division with this 4th degree and this 3rd degree guy, and I'm not feeling up to it right now, so we'll hold off on that for maybe a day when I'm stronger. Okay, so that brings us to the end of today. No, sorry, not the end of today. That's the end of this first half, and we'll have a second half coming shortly.